Watch this rocket land. Now watch it again. The date on the screen reads August 18th, 1993, 22 years before SpaceX made headlines with the same technology. A 40-foot metal cone rises into the New Mexico sky on pillars of flame, stops midair like it's forgotten the laws of physics, slides sideways like a helicopter, then descends and touches down on 4 spindly legs. No parachutes, no ocean splashdown, no army of recovery crews. Just a rocket landing like it's the most natural thing in the world. This was the DCX, the Delta Clipper Experimental. And what you just witnessed wasn't a special effect. It was real hardware proving that everything NASA believed about rockets was wrong. Here's the part that should make you angry. While NASA was hemorrhaging $196 billion on the Space Shuttle program, a small team at McDonnell Douglas built and flew this machine for under $60 million. $60 million, that's less than what some government agencies spend on office furniture. And with that shoestring budget, they proved the core concept of reusable rocketry in just 8 flights. So why have you never heard of the DCX? Because 3 years after that first triumph, a single missing part, a 25-cent cotter pin, would destroy not just this rocket, but the entire future it represented. This is the story of the spacecraft that could have changed everything, and the bureaucratic indifference that let it burn. The vision began decades earlier, in the mind of a man named Philip Bono. Throughout the 1960s, while NASA was building expendable rockets to reach the moon, Bono was sketching something different, single-stage to orbit vehicles that would operate like airplanes. Take off, land, refuel, repeat. His designs gathered dust in aerospace archives, dismissed as impractical fantasy. The math worked, the physics worked, but the will to build them didn't exist until Max Hunter came along. Hunter was a pragmatic McDonnell Douglas engineer who looked at the Space Shuttle with its army of technicians, its months-long refurbishment cycles, its expendable external tank, and asked a heretical question: why can't rockets work like airplanes? He called the DCX the most exciting project of my career, proving that rockets could be as reliable as airplanes. That statement wasn't just optimism, it was a declaration of war against decades of aerospace orthodoxy. The orthodoxy said rockets must be complex, expensive, and expendable. The orthodoxy said vertical landing was too difficult, too risky, too impractical. The orthodoxy was backed by billions of dollars in existing programs and thousands of engineers whose careers depended on maintaining the status quo. Hunter and his team were about to prove the orthodoxy was fundamentally wrong. But they'd have to do it without NASA's help. In fact, they'd have to do it despite NASA's skepticism. The funding came from an unlikely source: the Strategic Defense Initiative Organization. Yes, the Star Wars missile defense program. At the tail end of the Cold War, General Daniel Graham saw rapid, reusable space operations as a strategic asset. The ability to launch quickly, land, refuel, and launch again wasn't just efficient, it was militarily valuable. So he handed Hunter's team a microscopic budget and essentially said, "Prove it works." The design philosophy was radical in its simplicity. 4RL-10A-5 liquid hydrogen and oxygen engines, already proven reliable in other applications, producing 60,000 pounds of thrust total. Commercial off-the-shelf avionics, the same kind of systems you'd find in passenger jets. An automated flight control system that could land the vehicle without human intervention. No exotic materials, no billion-dollar custom components, just smart engineering using existing technology. Think about what this meant. While NASA's Space Shuttle required 3 main engines, 2 solid rocket boosters, an expendable external tank, and thousands of heat-resistant tiles that had to be individually inspected after every flight, the DCX was essentially a flying fuel tank with 4 engines and a computer. It was the engineering equivalent of Occam's razor. The simplest solution is usually the right one. But simple doesn't mean easy. Hunter's team was attempting something no one had successfully demonstrated: a rocket that could take off vertically, hover in midair, translate sideways, and land vertically, all autonomously. The automated flight control system would have to make thousands of micro-adjustments per second, gimbaling the engines and throttling them precisely to maintain stability. One miscalculation, one sensor failure, one software bug, and the vehicle would become a very expensive firework. And behind the technical challenge lurked a more insidious threat: institutional resistance. NASA wasn't just skeptical of the DCX, they were actively dismissive. Internal memos from the era reveal a culture that viewed the project as a threat rather than an opportunity. This wasn't just "not invented here" syndrome. It was something darker. The recognition that if this small team succeeded where NASA's massive programs had failed, it would raise uncomfortable questions about how the agency had been spending billions of taxpayer dollars. But proving the skeptics wrong would require more than clever engineering. It would require the vehicle to actually fly. And that's where things got dangerous. August 18th, 1993. The New Mexico desert shimmers in the heat as the DCX sits on its launch pad, looking less like a rocket and more like an oversized traffic cone. The McDonnell Douglas team has spent months preparing for this moment, knowing that a single failure will give NASA all the ammunition they need to kill the program. The countdown reaches 0, the RL-10 engines ignite, and the DCX rises on 4 pillars of flame. But this isn't like watching a normal rocket launch, where the vehicle accelerates skyward and disappears. The DCX climbs slowly, deliberately, then stops. It hovers. The automated flight control system is working exactly as designed, making thousands of tiny adjustments to keep the vehicle stable. Then it does something no rocket had ever done before. It moves sideways, translating horizontally while maintaining altitude, demonstrating the kind of maneuverability you'd expect from a helicopter, not a rocket. Then it descends, engines throttling precisely, and touches down on its 4 landing legs. The entire flight lasts just over 1 minute. But in that minute, everything changed. Pete Conrad was there that day. The Apollo 12 astronaut who had walked on the moon, who had piloted the lunar module to the surface of another world, stood in the New Mexico desert and watched this cone-shaped rocket land. His reaction, describing it as seeing the future unfold. Think about that for a moment. A man who had commanded some of the most sophisticated flying machines ever built, who had accomplished one of humanity's greatest technical achievements, was awestruck by watching this prototype touchdown. Because he understood what it meant. This wasn't just another test vehicle. This was proof that the entire paradigm of spaceflight could change. Over the next 2 years, the DCX would fly 7 more times, each flight pushing the envelope further. The vehicle reached altitudes over 10,000 feet. It hit speeds of 230 miles per hour, not orbital velocities, but that wasn't the point. The point was demonstrating that vertical takeoff and landing wasn't just possible, it was practical. Each successful flight was a middle finger to the skeptics who had said it couldn't be done. But the most impressive number wasn't how high it flew or how fast it went. The most impressive number was 26. The DCX team demonstrated rapid turnaround capabilities. They launched the vehicle, watched it climb and land successfully, then turned around and did it again in 26 hours. Not 26 weeks, not 26 days, 26 hours from landing to launch. Let that sink in. The Space Shuttle required months of refurbishment between flights, pulling heat tiles, inspecting thousands of components, essentially rebuilding parts of the vehicle. Here was Hunter's team rolling a rocket back to the pad, topping off the tanks, running through checks, and lighting the engines again before the desert sand had even cooled from the previous landing. They were operating a rocket like an aircraft. And it wasn't a fluke. They kept proving it, flight after flight. The economics were even more staggering. Each DCX flight cost approximately $500,000. Each space shuttle launch, over $1 billion. The entire DCX program, design, construction, and all 8 test flights, came in under $60 million. To put that in perspective, If the DCX program was a single grain of sand, the Space Shuttle program was a dump truck full of concrete. McDonnell Douglas was proving that the astronomical costs everyone accepted as inevitable for spaceflight were actually the result of throwing away perfectly good hardware after every mission. The data was undeniable. The technology worked. The operational concept worked. The economics worked. Hunter's team had done the impossible. They had proven that decades of aerospace orthodoxy was wrong. But success in the desert meant nothing without NASA's commitment. And NASA was watching with a mixture of fascination and dread. Because if the DCX was right, it meant NASA's entire approach had been wrong. It meant the billions poured into the Space Shuttle, the thousands of engineers dedicated to maintaining it, the political constituencies built around it. All of it was based on a false premise. So in 1995, NASA did something that seemed like validation but felt like a threat. They took over the program. The DCX was transferred to NASA and rechristened the DCXA. The A stood for advanced. The vehicle would be upgraded with cutting-edge composite tanks and Russian aerospace technology, pushing the performance envelope even further. On paper, it looked like the program was graduating to the big leagues. In reality, it was about to enter a bureaucratic culture that had a very different definition of success. The DCX had proven its concept under the scrappy, move fast and break things culture of the Strategic Defense Initiative. Now it would be tested under NASA's risk-averse, procedure-heavy management. The original McDonnell Douglas team, the engineers who had achieved 26-hour turnarounds, watched nervously as their creation passed into new hands. And on July 31, 1996, their worst fears would be realized. July 31, 1996. The DCXA, now wearing its NASA badge and sporting advanced composite tanks imported from Russian aerospace technology, sits on the launch pad in New Mexico. This is its fourth flight under NASA management. The previous three had gone well, demonstrating even more aggressive flight profiles than the original DCX. Today's mission: climb to over 2,000 feet, execute a series of maneuvers, and land. The countdown reaches 0. The RL-10 engines ignite. The DCXA rises smoothly, its automated flight control system working flawlessly. The vehicle climbs to 3,140 feet, higher than it had ever flown before. At the apex, it performs its programmed maneuvers perfectly. Then it begins its descent, engines throttling precisely, the computer making thousands of micro-adjustments to keep it stable. Everything is working exactly as designed. The team watches the telemetry. All systems nominal. The vehicle descends through 100 feet, 50 feet, 20 feet. The landing leg should be deploying now. 3 legs extend. 1 doesn't. The DCXA touches down on 3 legs, teeters for a heartbeat, then tips over. In slow motion, the way catastrophes always seem to unfold, the vehicle crumples against the concrete pad. The composite fuel tanks rupture. Liquid hydrogen and liquid oxygen mix. The fireball consumes years of groundbreaking work in seconds. The investigation found the cause immediately: a missing cotter pin. Let me show you what a cotter pin looks like. It's a small, bent piece of metal, roughly the size of a paperclip. Its job is simple. It slides through a bolt to keep it from unscrewing. Cost: 25 cents. You can buy them at any hardware store. This particular cotter pin was supposed to lock a hydraulic line in place. Without it, the hydraulic fluid leaked out during flight. When the landing gear deployment command came, there was no pressure to extend that one critical leg. A $0.25 part. A single missed checkbox on a pre-flight inspection. One tiny piece of hardware that should have been installed but wasn't. The engineers who had achieved 26-hour turnarounds, who had proven that rockets could land like airplanes, watched their vehicle burn because someone missed a step. But here's what makes this story truly infuriating. The real failure wasn't mechanical, it was institutional. Under the original McDonnell Douglas management, that pre-flight inspection would never have been skipped. The team that had operated the DCX for 8 successful flights had developed procedures honed through rapid iteration. They knew every bolt, every line, every critical component. When NASA took over, those procedures entered a bureaucratic system where accountability was diffuse and innovation was expendable. The missing cotter pin wasn't just a mechanical oversight. It was a symptom of a culture that had never truly wanted this technology to succeed. NASA had the data. They had the hardware. They had incontrovertible proof that reusable vertical landing rockets worked. The DCX had compiled 8 successful flights. The DCX-A had completed 3 more ambitious test campaigns. The technology was proven. The operational concept was validated. And NASA chose not to rebuild. They chose to move on. Instead, the agency doubled down on the X-33, a vastly more complex single-stage-to-orbit vehicle that would consume over $1.3 billion before its own cancellation in 2001, without ever flying. The X-33 would fail for exactly the reasons the DCX team had warned about. Trying to achieve orbit in a single stage required exotic materials and technologies that weren't ready. The DCX approach, prove the basics first, scale up gradually, was abandoned in favor of an all-or-nothing gamble that achieved nothing. Engineers from the DCX team described the atmosphere after the crash as one of intense frustration at lost opportunities. They knew that a simple checklist failure had destroyed years of groundbreaking work. They knew the technology was sound. They knew that rebuilding would have cost a fraction of what NASA was about to pour into the X-33's doomed development. And they knew that no one in power was listening. Years later, Charles Bolden, who would become NASA administrator, reflected, "DCX showed us what was possible, even if it was ahead of its time." It's the kind of thing people say when they're trying to soften a catastrophic institutional failure. Because the DCX wasn't ahead of its time, it was exactly on time. What it was ahead of was NASA's willingness to embrace a technology that hadn't been invented within the agency's own walls. A $250 part, 19 years of delay. And the question that still haunts the engineers who were there: what world would we be living in if that pin had been installed? Imagine an alternate timeline. It's the year 2000, and reusable rockets are routine. The DCX's descendants are launching satellites every week, their 26-hour turnarounds making space access as regular as commercial air travel. The cost per kilogram to orbit has dropped by an order of magnitude. The International Space Station was built faster and cheaper because launch costs weren't prohibitive. Mars missions are being planned not as distant dreams, but as achievable goals within the decade. That timeline was possible. The DCX proved it. The technology worked in 1993. The engineering was sound. The operational concept was validated. What failed was the system meant to nurture innovation. Today, when we watch SpaceX Falcon 9 boosters land on drone ships, when we see Blue Origin's New Shepard touch down in the desert, we're not witnessing the birth of reusable spaceflight. We're witnessing its resurrection. Elon Musk has explicitly cited the DCX as a direct inspiration for the Falcon 9. Blue Origin's New Shepard adopted its core principles: vertical landing, rapid turnaround, autonomous flight control. Every reusable rocket flying today traces its conceptual lineage back to that cone-shaped prototype in the New Mexico desert. The DCX proved it could be done in 1993. The world just wasn't ready to listen until SpaceX landed a Falcon 9 first stage on a barge in 2015, 22 years later. 22 years. Billions of dollars. Countless lost opportunities. Missions not flown. Discoveries not made. Scientific instruments that could have been launched but weren't. All because NASA looked at a working prototype and decided the future could wait. The real tragedy isn't the crashed rocket. It's the 2 decades of lost progress. It's the realization that bureaucratic inertia valued protecting the status quo over embracing transformation. It's the knowledge that we could have had routine, affordable spaceflight by the turn of the millennium, and we chose not to because the technology threatened existing power structures. Somewhere in a New Mexico desert, There's a concrete pad where the future once landed and took off again in 26 hours. It took us 20 years to return to that spot, not physically, but technologically. The DCX didn't fail. We failed it. And every time you watch a Falcon 9 land, you're watching the ghost of a 1990s rocket that tried to warn us. The future doesn't wait for permission. It just waits. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.